I think from Dirac's point of view at the time that he was writing that, that's what it looked like, because you had quantum mechanics having arrived there, and you had this mathematical framework of quantum mechanics, which was derived from classical physics, and then through the change of Poisson brackets to commutator, for example, where things were intrinsically uncertain. And it became a mathematical thing, and also the splitting of quantum mechanics to the areas which are involved in things like the the action, where you have variables. Of course, the fundamental uncertainty relation is really between time and inverse time, and we call it the energy-time relation. But energy is really related.
I agree, absolutely agree. That's the fundamental non-commutativity of the theory.
The thing about that is that that's only uncertain if that's all you know. And I think people have lost the way by thinking that that has to be some sort of built-in principle. But it's only uncertain if you're just making a single measurement. If you're looking at a wave in any kind of practical way, you're not making a single measurement. You know the damn thing's a wave. You know what energy it's got. You know all sorts of things about it other than the position and the momentum, or the energy and the time. Because you know maybe how it was created, how it's going to be destroyed because you measured it. So you know all sorts of things other than just the fact that you have a single measurement, which may be uncertain, or may not give you the whole information about something. Now, there was a huge, and I think this is where the physics has fallen apart, and I think it has fallen apart, because from the 1950s and pretty much from renormalization, you have this, I think, acceptance from Dirac through Feynman, although Feynman didn't like it either, and everyone else, that certain things could not be understood. And that began to fragment physics out. Now moved into all these tribes. We have sort of the Lagrangian theory tribe. The only thing you can do is find Lagrangian. For any given dynamics, you can find an infinite number of Lagrangians. Everybody knows that. I mean, just out of scalar potential, you can do all sorts of things, and there are different. But nonetheless, there's a whole tribe who does nothing else but that, and it's not fundamentals of how stuff works. So somebody can find a new Lagrangian, and they're off, and they can have a play and publish some papers. But this search to going back to how the stuff actually works is the way that everything did work up until the point where we had that quantum mechanics revolution. We had that difficulty there, where it became axiomatic that certain things could not be known. Well, Einstein didn't accept that, Maxwell didn't accept that, and I'm damn well not going to accept that. We want to understand how it works, and that's what we're about here. And we want more and more people coming in who are capable of getting inside things and pushing for that, and not accepting that it's something which cannot be simplified to something which is subject to human understanding. So yes, absolutely, I hear what you're saying there, and I
was just going to say that all this mythology about quantum mechanics has kept people away from the idea that quantum mechanics is the most exact form of physics that has ever been devised, and the most precise and perfect that we've ever come across, and the most perfect predictions.
That's right.
To all the rest.
I don't agree. Sorry, can I come in? I disagree. This is a very frequently made claim, but as I understand it, QED has been experimentally probed to something like 14 or 15 decimal places. Yep. GR has now been probed to exactly the same number. I think possibly even one order of magnitude further.
Can I come back on that too, once you've dealt with it?
Okay. Sure.
Can I also just make a point about sort of where physics went when we came to quantum mechanics? To me, I mean, in a sense, this is a criticism of physicists, and I think of myself as a physicist. The thing is, for physicists, real numbers are a religion. And, you know, when the 20th century hit, the language of science was differential equations and then differential calculus. And when stuff started coming out being discrete, everyone went, "Oh, this is very confusing. We better make it continuous again." And so matrix mechanics became Schrödinger's equation, and we've stuck to that religiously in physics all the way through, because we're comfortable with real numbers and differentiable manifolds and all of the stuff that comes in. And in the end, I mean, look at the stuff that's happening on a Quicycle. I mean, some of us now are a bit more comfortable with counting, which you can't do with real numbers, than we are with real numbers in the end. And so we're going back to try and come up with a language which is, in a sense, closer to nature. And I think this is just something that, I mean, it's to me, it's a continual tension within physics that the language, we keep trying to make the language fit with nature, when in actual fact, we will probably be better off to start out with the discrete in the beginning, so we could see where a lot of this stuff comes from. And so Dirac's comment about, we're going to have to go to more and more complicated mathematics to understand physics. To me, I think that was, in a sense, a nod to the fact that, well, okay, if we're going to proceed with the same sort of language that we're used to, yes, that's what it's going to be like. But that wasn't a comment or a thought that included the fact that, well, maybe we should step back from the language that we use and examine the language itself to see whether it really is sort of the most appropriate language for dealing with nature.
Well, we can try to do that, but it's not easy to say, oh, I'm just going to be discrete, nor is it obvious that that kind of discrete, which would approximate to the continuous, is the kind of discrete you want. It may be that the kind of discrete you want is to understand that the algebra is coming out beautifully discrete, like Peter's algebra comes out beautifully discrete. There it is. And there's a way to combine that with the continuous as well. Yeah, there are a lot of different points of view here, and we have no uniform language. The one that we inherited from the 19th century of how to do limits is the one that all mathematicians have been trained to do, and is very subtle and not necessarily the one you want. I'm talking about Cauchy sequences and reals and all that, right? But there are lots of alternatives, and nobody has found the alternative that's going to work for physics at this point. So so what you raise is a really great question. That's all I'm saying. It's a great question. Yeah. What would be the right mathematical language?
I think we need to keep in mind that if one's looking at a mathematics, we should also be thinking about a process. What is the process by which things occur? What is the ordering in which things occur? Can we get our mathematics? So looking at both the nilpotent and the idempotent in terms of the two different sides of looking how something doesn't change to something else and something is unchanging. Keeping those, because both have to happen. Both have to happen. So looking at one thing in terms of process, and process, computer scientists are very well used to looking at digital systems, where something leads to something leads to something else. And in that kind of sense, that's a good way of looking at what's going on. Let me quickly answer Michael's original thing about quantum electrodynamics and just say why it's so wonderful and why it's so terrible. It's wonderful, of course, because it has no contradiction with experiment, and because it gives results for G-2 to 10 decimal places and so forth. It's terrible because of the way
16, I think.
Okay. 95. I'll give it as many as you like. So far, no discrepancy with experiment at all. But that's because right. But where's the uncertainty principle? You're talking about things where you're looking at probabilities of an electron. What is quantum electrodynamics at root? It is a very simple theory. Okay, there's some pretty nasty maths there. But essentially, all it is the probability that an electron may emit a photon. Okay, and the probability, or a charge may emit a photon. That's all that's in there. The rest is counting and geometry. Now, that probably means that quantum electrodynamics is correct in that there is a certain probability with which a charged particle may emit a photon, and that's combinatoric, and you can look at all the different length scales and the distances over which that can occur. But that's all that's really going on there. That's not wrong. That's absolutely right. But it's starting from a position where you already have the charge, where you already have the elementary particle. Now, okay, From that point, it's utterly perfect and not in contradiction with experiment, but it puts a complete blank down below that, a complete blank below what the electron is. It puts also a relationship between the electron and the photon, the electron being a particle and the photon being an intermediator of the electromagnetic interaction. It puts shutters down on your mind and thinking anything down below that. The fact that it's perfect calculationally obviously has to mean that any theory which one develops has to give its starting point. It has to derive it if it's going to be a part of science that should be correct. But it's a horrific approximation when you start looking at elementary systems, at elementary particles and elementary photons. And also, it doesn't obey it's not quantum mechanical in the sense that it doesn't obey an exclusion principle. If you're looking at the electrodynamic interaction between a particle bouncing off another particle, you know exactly where they are down to 10 to the minus 18 meters. You know exactly the position. You know exactly the momentum, 200 GeV. Try doing that sum and see where the uncertainty relation comes into that. It's nowhere. So it's not quantum mechanical in that sense. It's a different kind of theory, and it's a beautiful theory, but it's not the whole story. It's a part of the story, and a beautiful part of the story. But what's missing is any kind of fundamental understanding at the level of knots, which Lou's interested in, at the level of how particles fit together, at the level of what the hell things are. What is an electron? It's not saying it. It's only saying that it is, not what it is. Sorry, that was my long spiel there, I know. But
can I just say one thing very, very quickly about the whole issue of whether we have to start from the discrete or one thing very interesting in that point of view, which I might summon my courage and think about giving a talk about. It'd be very much a second-hand talk about other people's ideas, which is the whole idea of minimal parts geometry. There's a neglected tradition which goes right back to the Greeks, which I think has recently been revived, of seeing whether one might sort of reformulate. I'm looking at this tension, which has been there at the heart of mathematics since the beginning between the continuous and the discrete. Whether one way of resolving it might be to explore ideas about so-called minimal parts geometry. I mean, irrespective of that, it seems to me that we're not going to get to the bottom of these issues in, what's the correct starting point in physics. Without bringing in the further question of what are the correct starting points in mathematics. And that still seems to me to be a very, very open question. So that we really ought, I think, just methodologically to stick with the, let 100 flowers bloom philosophy at the moment, at least in pursuing mathematics and the kind of mathematics that we need for physics, which is what I find so interesting about Lou's work.
I agree completely, Michael, and I think that's very well put as well. Thank you very much indeed for that comment. And I think we as a group do realize that mathematics is stuff we make up, it's stuff we invent, it's flexible. And we're looking at mathematics that disagrees, all of us, with our own mathematics some of the time, just to have different ways to look at this.
Yeah,
it's one thing, it's part of the of understanding. And
this is one reason why I found some of Lou's work about on foundations of calculus from the point of view of not topology and non-commutativity, and his discussion about how we might modify, for instance, the Leibniz rule. I mean, so fascinating. Those, I think, are the kind of ideas that we should be exploring, looking at the foundations of mathematics with, as it were, our physicists, our interest in the foundations of physics, with that hat still on, but perhaps slightly in the background. That's not too complicated a mixed metaphor.
Or another comment about different ways of discretizing. What I was doing today earlier when I talked about the knot diagrams, they discretize the whole problem, the topological problem of movement of rope, continuous rope in space, are discretized perfectly for topology's sake into these little discrete diagrams and special moves on them. So it becomes a graph theoretic description. But it's not approximate, it's precise at the topological level. At the physical geometric level, it doesn't capture certain things. Like, suppose I want to know the least length of rope needed to make a knot. Well, those diagrams don't tell me anything. I have to think about the geometry of the rope, the thickness, the bending, all sorts of other things. But for the topology, it's as perfect as anything can be. So you may find that for a given problem, there's exactly the right discretization of it, but you never knew it before. You had to find it. It had to be discovered.
Yeah, I think Garnet's work as well has been exciting me quite a lot in terms of bringing in digitization that introduces an extra feature over and above the 1, 0 or -1, +1 element, where you bring in something which introduces a loop, which introduces something which is recursive. And I think that recursiveness in nature, the fact that stuff comes back to itself, is utterly crucial to understanding things that persist. And looking at that from the foundations of what mathematics must have.
Yes, you made a very interesting remark in that connection about idempotence a little while ago, which I'd love to press you on, perhaps another time.
There's a lovely talk Peter gave. I forget how many times ago it was. Was it the talk before last where Peter was talking about the relationship between nilpotence and idempotence? If you've not seen that one yet, go back.
No, I haven't. I'm afraid I haven't caught up with Peter's talks. I mean to do that perhaps in the next couple of days. Yeah, thanks. Okay, all the best to everybody. Thanks for a great talk. Really enjoyed that. That's absolutely fascinating.
See you next week.